In this video, I'd like to show the new profiling and benchmarking tools available in Axiom 2.2. If you look at the debug mode on the solver, you'll notice that there is a new profile option. This will enable the solver to record information about the last time step that ran. You'll find a new detail attribute on the output of the solver that contains this information, and because it's a detail attribute, if you save with your caches, you can look at a specific frame later. The profiler tool itself is a Python panel, so we can go and grab a floating panel, go to the Python panels, and find Axiom's profiler as one of the available tools. This shows timing information for the current time step and when certain events occurred relative to the start of the time step. You can zoom in and drag the view around to look for a specific area. Then you can hover over the timeline to see what each step is and how long it took. You can also click and drag in the timeline to measure a custom range. Each row gives you different information. The input and output tabs will tell you how long the solver spent reading and writing VDBs, for example. The solver row shows you the CPU work being done by the solver. For example, you can see the project non-divergent and advection steps. Remember that this isn't work being done by the GPU, this is CPU only work, which is why it looks very sparse. The script row shows what stage the solver is in. Prescript is running steps related to the sparse data structure and preparing data for the various steps of the solver. Postscript handles the tasks after the simulation is done, such as downloading the grids from the CPU for export. And script is the solver itself, such as forces and advection. Finally, you can see the queue row, which tells you when the CPU is waiting for GPU work to be done. Now I can show you how I use this to debug and test performance optimizations. Let's take the VDB output as an example. Maybe I don't need all these grids, so let's disable velocity grid and rerun the solver and see how it changed. You can see that writing the VDBs is now faster because there are less grids, and the postscript is faster as well because now it does not need to download the velocity grid from the GPU. When you're just dialing in settings, it'll be faster to disable the grids you don't need until you're done and need to do the final cache. You might also be wondering why the VDB is being written out during the simulation step and why postscript comes before script itself. The reason is that Axiom simulates one frame ahead in the timeline, so the frame being downloaded and written to disk is actually the last frame's work. We can change this in the parallel sim and output setting to the output after sim setting to see what effect it has. Now you can see that the grids are downloading from the GPU and the VDBs are written out after the simulation steps. By doing a sim step and writing the VDBs in parallel, we can hide the time it takes to write out the sim, making it faster. There's some information we can't see easily due to limitations with OpenCL, but with Metal on macOS, you can get a more detailed view about what the work the GPU is actually doing at any given time. So that's the profiler. Next up, I'd like to show the benchmarking tool. In the object context, you'll find a new benchmarking node. This lets you run 4 different tests based on the cathedral tower scene I've created. You can pick a specific test, pick which compute API you want to use. I'll pick OpenCL since Metal only works on Mac. You can also pick a specific device just like on the solver. Then you can hit run and get some statistics. So what this tells me is what test that was run, what API was used, and how much memory it used. All tests will use 5 GB so that it can be run on the greatest number of devices. You can see what device it was ran on. You can see the time it took to complete. You can see the average performance in terms of voxels per second, and the maximum number of voxels the solver used. This is useful to gauge the health of the device, as I like to call it. If this number is much more different than other devices I've tested, that would indicate some problem with the device, such as an issue with the driver, for example. I put together a page on my website that shows the stats from all the devices I've had access to, and you can submit your own results as well for me to see if you'd like. This new tool will help me better debug devices that may be acting up, and is also a new way to measure device performance in a more standardized way.